thanks to Adrian, we're sitting here, or are you together, because Adrian really insisted in us doing that. And I think it's a good thing for us to get together to talk about mainly about C++, but mostly from the perspective of HPX. Over the last years or so, we have made the experience that when people work with HPX and they have problems with HPX, those problems have been, well, mostly have been because of them having problems with C++ and not with HPX. People who know C++ well usually don't have any problems with HPX in the first place. And we have good evidence for that. Several people just came in, started working, and had no problems whatsoever to use it. That's why the idea is to talk about C++, about the techniques we use in HPX, which are very specific to C++, and how they work, and how what language features are applied to that. That being said, I have no strict plan of what to talk about for the next couple of weeks every Thursday. I know what I want to talk about today, but I don't even know yet what we want to talk about next week. So I'm saying that just to give you an idea that I really would like that to be interactive. We've done that last summer, right? You've been there, or 2 summers ago or something, where we have been talking about that, and that worked very well because we did it in a very interactive way. Okay, so let's first start with, or what I wanted to start with is to tell you why I like C++ and why I want to use C++ for the things I'm doing. You could say, hey, that's one of the most complex languages around. Why did you choose that one and not any other language which might be easier to use? Well, there are 3 reasons for that, why I want to use C++ and why I think that C++ is the right language for this kind of work we're doing. First, it allows us to get at the bits in the machine. So in some sense, it's a very, very low-level language. It allows us to manipulate single bits. And that's very important because sometimes you really want to get as close to the hardware as you want, as you need, and in order to do things. This is something you can't do almost with any other language. Sure, there are languages like C and nowadays Rust and so on, but those are very similar languages. Most of the languages, most of them have no means of you directly talking to the hardware. The second reason why I like C++ and why I use it for my work is it is a language which gives you the ability to build very high-level abstractions. Very high-level abstractions. And but the caveat is, and that's the third reason, you're building these high-level abstractions without paying a runtime performance penalty. So you can build abstractions in C++ which doesn't cost you any runtime performance. And the combination of these 3 things is what makes C++ unique. It's almost the only language which gives you these 3 capabilities. And it's definitely the only mainstream language which gives you these capabilities. The only language which I know which it would give you that as well is a language called P, which was designed to overcome some of the idiosyncrasies of C++. It has its own community and people do work with it, but it's by no means comparable in terms of market share to what C++ has. So that's why let's focus on C++. If you look, low performance. The third reason was that you can build these abstractions without runtime performance penalties. That doesn't mean that you don't pay anything, right? There's no such a thing like free lunch, right? Nobody has invented that at this point. The cost you're paying is compile time. So you have to, it takes longer to compile the code in order for the compiler to be able to optimize away the abstraction layers you introduce. But that's a cost I think we should be able and should be willing to pay, because you compile it once and in the end you run the application much more often than you compile it, at least once you have reached a certain stability in your application. Each of you probably had some C++ classes or some C classes in, well, C++ classes in undergrad. You might not.
I don't see.
C. You know, the problem is that your C class probably was not different from the C++ classes other people had. In other words, I'm pretty sure about that. In other words, the way C++ is taught today is by taking C as a basis and talking all the semester long about arrays, pointers, and all these nice idiosyncrasies. And in the end of the semester, they say, hey, by the way, there's something you can build more things with it. You can build structures and classes and all that stuff. But that's kind of a bythought. So nobody's really talking about C++ from that end. Everybody's teaching C++ as C was classes. C was something on top of it. Just to give you an idea, I talked to one of the main professors here at the CS department at LSU about C++. And he said, yeah, I know C++. It's a cool language. You just take your C program, write class, a brace, and the brace in the end, and you're done. I said, really? Okay. Professor at LSU. So just to give you a sense what the understanding of C++ and the professorial faculty. And LSU is not special in that regard. I believe C++ has to be taught the other way around. It has to be taught as a language which gives you higher level facilities. And in the end, and that's what I do in my classes when I teach C++, essentially I introduce pointers in the last lecture. And I introduce them mostly because I have to, because otherwise they will beat me over the head in the CS department. You can get very, very far with C++ without using a single pointer in your code. And whenever you are tempted to write a pointer, think again, you don't need it. There is no need for pointers. Whenever you want to write pointer, you're doing something wrong, or you haven't thought it through. If you look at the at the source code of HPX, you will be hard pressed to find pointer. There are some, but they are very well justified why we did it with pointers there. And if you have to use a pointer, then please always wrap it into a type which it tends not to be a pointer. And we will talk about that, how to do that. You might say, hey, why am I so adamant about pointers, not using pointers at all? Well, the reason is that 99% of all security vulnerabilities in industry are caused by people thinking they're more intelligent than they are. And they were using pointers for their code and they just screwed up. So almost the overwhelming majority of all problems in C code and C++ code are caused by people not dealing with pointers properly. And that's why just get rid of it, and you get rid of 99% of all possible bugs you might create in your life. And that is a good thing, because you don't want to create buggy code. You don't want to debug things which are so difficult to find. And you know, that bug we are chasing was Dominic's code. I'm almost certain at some point I've lost that. And we are chasing it for half a year now, for 6 months, so we're not able to find it. Okay. So that's kind of setting the stage of how I approach C++ and how I want to talk about it in the context of these small sessions. What I also want to do, I want to talk less and more code examples. That's why I want. I don't know why it's off. Probably my computer went to sleep. Yay. Let me quickly tell it first. Okay, so okay. Yeah, less talking, more coding. I want to really do all the things I will present just based on examples. Just write some code. You might have some ideas what we want to implement, and we're kind of writing code and showing these concepts I want to. Okay, so let's start today. What I wanted to start with, and it really forced me to use that piece of paper here.
And you want to switch the
computer. That's kind of annoying, but anyway. What I want to start talking about, and I guess when I'm sitting here, the sound is probably as bad. That bad. That's probably. So it works. I want to talk about STL, which stands for Standard Template Library. And this Standard Template Library consists out of 3 parts, and I will talk about those in separately. One is containers. Algorithms. And the connecting piece are iterators. There are 2 more pieces, but those are not that important in this context. Anybody old enough to have read Niklas Wirth's book, Algorithms plus Data Structures equals Programs, or the other way around, Programs equals Algorithms plus Data Structures? Probably not. You haven't been born when Pascal was a language, right? Niklas Wirth is the inventor of Pascal, Operon, and other languages from that class, which are very were widely used in the 70s, essentially, for teaching programs. But the book he wrote, Programs equals Data Structures plus Algorithms, is more up to date than you would think, because that is really all what programming is about. Programming means finding the appropriate data structure to store your data in, which models the reality in the context of your code, and writing 3 for loops around it and do some stuff. So in a broader sense, 3 for loops as algorithms, doing something with the data in Twitter, right? Traversing the data, replacing things, looking at it, finding things, and so on. So certain ways of dealing with the data. And once you have your data structures and you have your algorithms which deal with those data structures, you have exactly the program. That's why containers, which are the data structures of the standard template library, and algorithms is the code we can use to deal with them. And iterators, and I will talk about iterators more, are what ties them together. Emotion. You want to continue? He knows it better than me. So no. Okay. If you look at the code first of all, standard template library is a library. So it's not a language feature, but it's using the C++ language to build higher-level facilities you can use in your code. If you compare the standard template library, which was, by the way, invented in 1995 by Alex Stepanov, also should ring a bell. He's reading the book, or was reading the book, you as well. Stepanov, the author of that book we've been looking at. He invented the STL in 1995, or a bit earlier, 1992, and it was added to the standard in 1995 and finally standardized in the first time. So what's so special about the standard template library? The standard template library is a generic library. It is built around generic programming techniques. Anybody heard what generic programming is? Have you heard that term? Yeah, what is it? What do you think it is?
Templates.
Okay, templates are the language feature used to build generic code. But what is generic code? Why it's called generic? Not because it's using templates.
Abstract.
It's abstract, okay. Abstract from what?
Underlying data.
Right. So you write code independently of the data types it's applied to. You write algorithms which don't know anything about the data structures you work on. You write code which is usable with any data type the user might supply. You write an algorithm which works with anything which people will come up in 20 years from now. Right? And that gives us that very flexible way of thinking about the algorithms, thinking about dealing with data without having to deal with or think about what is the data I'm manipulating. When I'm copying things from A to B, then I don't care what is the data type of the things I'm copying from. Right? Copying just means I take whatever I have and move it over to it or create a copy of it in a different place. So the copy algorithm itself doesn't have to know anything about the data type it's working with. All it has to know is how to move things from it. So you abstract the actual operation on the data from the data types. If you look at other libraries which are around for Java, for instance, we will have containers there. You have lists, you have hash maps, you name it. But each of those data types, or each of those containers, has a whole set of member functions: sort, copy, clone, transform, whatever, right? 50 of those member functions, which are implemented on a list, on a hash map, on a tree, on whatever. So in the end, if you have 50 algorithms and 10 data type, 10 containers, you implement 500 algorithms. Whereas in the standard template library, because things are independent and containers are independent of the algorithms, you implement the algorithms once if you implement the containers once. So you don't have 500 algorithms, you have just 50 algorithms and 10 data types, 10 containers. And that makes it so nicely orthogonal. So the algorithms don't know anything about the containers, and containers don't know anything about the algorithms. And that has a nice side effect that if you figure out, hey, I need an algorithm which is not standardized, which is not in the standard, which is doing things differently than from what I actually, well, the things I need are different from what is implemented. You just implement a new algorithm and use it with predefined container types. And vice versa, if the containers don't support what you actually want, you might want to look into, right? You want to find the best possible way of looking up things in HPX and AIS under certain circumstances. Then you will use the standard algorithms, but you might want to come up with your own data type, with your own container which stores things. So the stuff which was invented 30 years ago almost still works very well, and the algorithms which were invented at that point work perfectly well, even with containers I develop today. Well, these two things can't be completely independent because in the end, the algorithm has to do something. The algorithm has somehow it has at least to be able to refer to the data it's working on. the copy algorithm has to identify the data items it copies. And this connection is achieved through iterators. And iterators, in a general sense, you can think of them as a data type a type referring to an item in a container. So it just refers to one element in a container. If you have an array, it refers to one of the elements in your array. And that gives copy the ability to say, okay, I want to copy that thing this iterator is referring to. But copy itself only works using the notion of an iterator. Iterators are, in some sense, generalized pointers. So if you know what a pointer is in C++ or in C, you perfectly understand the semantics of an iterator. Pointers are special iterators, and we will see that you can use all pointers directly with standard algorithms. So if you have two pointers which point to the beginning and the end of the range of an array, you can pass those to the copy algorithm, and it will work just fine. Okay. So let's see. Does it make sense so far? I think so. Shouldn't be difficult to understand. One last thing I want to say about that general approach is that in order to make that work, two things or several things have to be set in stone. A, all containers have to expose certain functionalities which are uniform across all containers. For instance, a container should be able to give you an iterator to its first element and an iterator to its last element, so that a copy algorithm could just span the range of all elements. That is a property all containers have, right? And all containers, well, I hope you know what a container is because nobody asks, right? A container is a data type which stores more than one element.
The graph.
The graph is a container.
How do you know the first element of the graph?
Oh, the graph has to know. You can arbitrarily decide that's my first, that's my last, and when you use that iterator, you can traverse the whole graph until you get to the end. How it does that and how it figures out that there are no cycles and this kind of thing is up to the iterator. But in the end, you have a first and last one because it's finite, right? So you can find a way to represent
All pointers have to expose certain functionality.
Yes.
So what?
begin and end.
Yeah.
Usually they expose how many elements they have. They have a size member function which gives you the number of elements they currently store. They usually give you other functionalities like whether they are empty or not. They give you functionality to add new things to it or remove things from the container, push back or pop back in the simple case, insert. So these functions, and they are all named the same, and that's very important. So all containers expose the same functions, which are named the same, have the same spec. On the flip side, all algorithms are written in terms of iterators. And what algorithms usually expect you to write them with is a so-called range. It's two iterators, one iterator pointing to the first element, and one iterator pointing to, oh, not quite to the last one. The end iterator always points to the element after the last one. It's important to remember. And let me just draw that for you, so you understand why. If you have a simple array, and we know that things are consecutive in memory. So the first element is just this, and the end iterator will point to the last element, to the first element after the last one. And the reason for that is you can deal and think about open ranges in much better ways than about closed ranges. For instance, if I have an open range, B, E, what is the size of that range? How many elements do I have in that range?
Minus B.
Minus B. So the size is E minus B. But if I have a closed range, what is the size?
Minus C++.
Right. Which is kind of awkward. How do you write an empty range when you have open ranges? An empty range, which has no elements.
C equals
An empty range is just this, right? How do I write an empty range with closed ranges? Right? So there's no way to represent a closed range, an empty range in a closed range syntax. And that's the main reason why all end iterators which point to the end of a sequence, always point to the element after the last one. And that's important to understand and always to remember, which implies that I shouldn't use an end iterator for anything but comparison, because it doesn't refer to anything real. It just refers to some imaginary spot somewhere in the universe which doesn't exist. Okay. Yeah. So let's talk about iterators in the first place, because that is an important concept, and I want to drill in there a bit. In order to make iterators useful, and in order for algorithms to be able to deal with containers, iterators have to expose a certain functionality as well. It's a functionality the algorithms can rely on. And A, B, as it turns out, there are different categories of iterators. And these iterators with different categories have different properties, have different capabilities, so that you can write some algorithms require only very weak iterators. I'll give you an example in a minute. And other algorithms require much more stricter things from the iterators in order to be implementable. For instance, if you look at the copy algorithm, all the copy algorithm does, it looks at the current element, copies it, and then it moves to the next one. Copies that element, moves to the next one, and so on. So it's a very weak iterator, because all it needs is essentially retrieving the element, writing the element, and increment, go to the next element. Whereas a sorter algorithm, for instance, is very strict, has very strict requirements, because it does much, much more. It has to compare arbitrary elements in the sequence. It doesn't only jump by one in one direction. It might jump arbitrarily back and forth in order to compare the proper elements in order to get the sequence in order, right? You have to swap elements in order to sort them. And for that, you look at two elements, say, okay, that one is actually smaller than that one, so I swap it in places. And then I repeat that process until everybody's in sorted order. So these categories of iterators are very important feature, and in fact, they came up with a so-called iterator category hierarchy, which I want to highlight. Let's start with the simplest iterator, which is called an input iterator. Is it visible? Oh, something happened. Yeah. Great. Thank you. An input iterator supports only the most trivial operations. First of all, if I have two input iterators, I and j, I should be able to compare two iterators for equality. What does it mean that two iterators are equal? What would you expect? If I have two iterators which point somewhere into a sequence or into a container, What does it mean that two iterators are equal? They point to the same element, right? It could be two iterators, but they point to the same element, then they are still equal. So I have to be able to compare two iterators for equality and for non-equality. Because in the simplest case, again, our copy algorithm, when I go through the sequence, I have to know when to stop.
But how do they know what the next one? That they're going to follow the same. If they're not iterating in the same direction, for instance, I still would call them the same iterator even if they're on the same.
No, when they point to the same object, they are two iterators are equal when they point to the same object. It's like pointers in C, right? You have two pointers pointing somewhere in memory. The pointers are equal when they point to the same memory address. No matter what you do with them afterwards, it's really just equality. And you need that in order to be able to know when you're done with the loop, right? Just go over from begin to end, and in order to know when you are at the end, you have to compare with end iterator. Okay. So, and the second thing we said, you need to be able to access the element. So we need to dereference an element. Dereferencing. And if you know pointers, then you will know the syntax. Just putting a star in front of a pointer dereferences thing and accesses the element the pointer the iterator is referring to. But since it's an input iterator, that dereferencing is allowed only on the right-hand side of an equation, of an assignment. So you're only allowed to read through that, you're only allowed to read the value. And the last operation which we need is plus I. Move to the next element. That's it. You might say, hey, that's not useful. Why do I need that very weak iterator? If you create, or if you define it that way, essentially reading from a keyboard can be represented by an iterator. Because reading from a keyboard, you can't write to a keyboard, you can only read from it. And moving to the next one means discarding the current value you got from the keyboard and waiting for the next value. So you can use an iterator which represents the values, this data stream which comes from the keyboard. That also implies that you can't go back in time. You can't take a copy of an iterator, point it somewhere, move the copy forward, and then go back to the one before. Because, well, it's a keyboard input stream, right? You can't go back in time. You can't go back to the keyboard input you had half an hour ago. That doesn't make sense. If there's an input iterator, you obviously have output iterators as well. And as you already might guess, what you need is equality. You need dereferencing, but this time only on the left side of the assignment. So you're not allowed to read from it, you're only allowed to write it. And the best example for that is putting characters onto this display. And once you put them there, you can't read them back. And also you can do ++, which means move to the next position on the display so you can put the next character. Yes?
Oh, okay. You don't have to read it.
You don't have to read it.
Yeah.
And you can't go back in time, so you can't store a copy of it and move forward and then go back in time and overwrite things on the display. Okay, that's why it's a very weak output. Okay, let's build a bit more complex things. The next category is called forward iterators. Okay, what do you expect from a forward iterator? What operations? Which is a bit stronger than these very weak iterators we have. But first of all, probably equality, right? We need that always. You want to be able to dereference, but this time you want to read and write from it. You want to increment it by 1. And what you want to be able to do, you want to be able to take a copy and go back in time. So you want to be able to say j equals I plus I, and then reassign, go back in time, and compare with j. So, and that is very, very nice because I can just repeat my operation on my input data sequence over and over again.
So which SQL container outputs an input iterator but not a forward iterator?
There's no container exposing it.
So always primary container you can get a forward iterator.
Any container, and I will talk about that, any container at least exposes forward iterator.
If I had a case when I had to use, I couldn't use an input iterator, but I was wondering if it's possible for a user to get an input iterator.
Sure. Sure, you get an input iterator by wrapping C in. It's called stream iterator.
I for the input output from just for I.
Right, it's for I. Well, as you might guess, the next step is a bidirectional iterator. Which can do the same thing as before, quality, dereferencing on both sides, plus I, and it can do minus I. So that means you can not only go in one direction through the container, but you can go in two directions through the container and go backwards and forwards from the current element. I might not have said that, but incrementing an iterator means moving to the next element in the container, which is obvious in an array for C pointers, right? When you increment a pointer, it goes to the next element in the array, points to the next one. And if you decrement it, it points to the previous one, which is for arrays for sequential memory layout is trivial to understand because it really just jumps to the next memory address after the current. For other containers, it might not be as obvious because if you have, for instance, a bidirectional list, everybody knows what a bidirectional list is, how that works. Do you know what a bidirectional list is? Why don't you say so? I'll get to that in a second, and you will understand that. Let me just finish the hierarchy here. The last one is a so-called random access iterator. And this iterator exposes the same functionality, but additionally it exposes plus equals n, minus equals n, and indexing. And from that, you should see that a plain pointer in C or in C++ is nothing else than a random access iterator, because all these operations are defined for a plain pointer. In that sense, a plain pointer is just a special iterator, which does not point to an element inside a container, but which points to an arbitrary memory address into your address space. Okay?
Just to make sure forward iterator is both readable and writable.
Forward iterator as well?
Is both readable and writable.
Yes.
Unless you
Yes.
have a
Because
concept.
Yes. Yes.
So that is what?
Unless you have a concept.
Well,
Okay. But no, but the reason is because it inherits from both. Because there's both input iterators.
yes.
Okay.
Each iterator of a stronger category inherits all properties of the weaker iterators. So a random access iterator is still an input iterator or still an output iterator, but not vice versa. So all properties of an output iterator are possible for random access iterator. So you can dereference it, you can move it back and forth, and you can jump back and forth. Okay. C++ 17 has, I believe, two additional iterator categories, a weak input iterator and a weak output iterator, which are in the middle of input iterator and forward iterators in the sense that you can still use it only on the right-hand side of the assignment, but you can go back in time. So you can take a copy, go back and repeat the sequence, but you can only read from it. For certain range operations, this is useful, and the same is true for output iterators. There might be a weak output iterator category which goes in between. So we will not have 5 like today, but 7 categories in the future. Okay, so let's talk about data structures. And you said you don't know what a bidirectional list is, so I apologize if I am talking about things which you might already know. Let's go back to the question Martin had. What containers do expose these iterator categories? And there's a clear relationship between the containers and the iterator categories they expose. As already said, the first two, there's no container which exposes these weak iterator categories. But there's a container which exposes a forward iterator. Which one is that? Anybody knows that? Forward list. It's called forward list, standard forward list. And a standard forward list for you, for John, is the following data structure. It can store arbitrary elements of a type T, and it stores the pointer to the next node, which is somewhere in memory only. So when you have a iterator to the first element, all you can do is go to the next element in the list. You can't go to the previous element without starting over from the beginning. There's no way to do that. And in a forward list, incrementing an iterator means moving the iterator to point to the next element in the list. And since these nodes in memory can be arbitrarily distributed, they are not consecutive anymore. First can be here, the second one there, the third here. So it jumps back and forth in memory. When you increment the iterator, it will follow that chain as the container is built. So you traverse the container in the sequence of their elements. And in that sense, incrementing an iterator suddenly gains a completely new understanding, because it doesn't just mean move to the next element in memory, but it really means move to the next element in my data structure. You don't care how the data structure is built underneath. Okay, okay, a bidirectional list. You might already have guessed it. A bidirectional, there's what bidirectional containers we have. We have a container which is called standard list, which should have been called bidirectional list. And the difference to a forward list is that each node stores not only the pointer to the previous one, but to the next one, but also the pointer to the previous node in memory, which allows you to go back and forth through the list when you have an iterator to an arbitrary element. Okay? By the way, a very widely used interview question. You have a forward list. You have an iterator to one element in the middle of the forward list. How do you delete that element? How do you get rid of that element? How does it work? How would you do that? If I ask you to write a code which takes a forward list and removes that element from the forward list. Let me draw it again. So I have this kind of data structure. And all I have is a pointer to the middle element. How do I remove that? In order to remove that element, I would have to change that pointer to point here. That's all I have to do. I just take that pointer here and make it point to the last element. Well, I know the iterator to that one because it's stored here. But how do I access that one? How do I write that new value into the previous node? How can you do that? No, you have a forward list only.
But you have only iterator or the...
You have just the iterator. Nothing more.
You can, because for internal, you cannot access internal structure of.
Well, let's assume you can access internal structure.
And then with this whole pointer of that whole elements, we evaluate that one, if they wanted it in the middle, and then once we got to the last elements, we point it to the,
Well, there's no way to get here.
well, you said you can see the internal, it is.
Yeah, sure. Even if you see the internal data structure, you don't see that where that node is.
Can you create
Oh,
a
we
new
have
character
that.
at the beginning?
No, you don't have that. Well, if you had that, it would be right.
But we can expose the data. So.
Well, let's
So we can.
let's
we
say
can-
it's
we
it's
get
just
to the
plain
next one,
pointers
and
and
then copy.
Yeah, that's what I was gonna say. Copy
Right,
the next.
right.
Copy the next, and then
You
actually
copy that
delete the
one.
next.
then you copy that one, then you copy that one and delete the last.
Like, do we even have to do that?
You have to do that.
Why can't you just delete the? We have access to the next one.
pointer.
Yeah, sure. You want to get rid of that one.
Sure. Yeah, why can't we just? It would be easy right now to delete the next one. If you set up this question and said delete the next one, could we not do that with?
Yeah.
We could just remember, and so that's what I'm saying. Instead of deleting all of them, just
You're not deleting them. You copy that one over.
yes, and you
Then
delete the
you
last.
copy that one over.
Sure, I'm just saying.
And
keeping
the
the-
last one
Yeah,
gets
if you
deleted.
have the point of the previous one, it was easy, just.
You don't have the point of the previous one.
We can't just. Oh, we can't create a pointer. Well, the one that we're at is the previous to the next. That's why I'm asking.
No, he's saying the pointer that we have is the pointer to what we want to do.
And I'm saying copy it the way he's doing, but he also says copy every element in the list
Okay, if I just copy that one.
and then delete the next one. Now I delete that.
Okay, and I could just
And then I don't have to.
rewrite that. Yeah. Right, okay. You
That's
could,
fine.
I could do that. You're right, yes. So it's a, if you ever get that interview question, you can just answer.
Is that
So it's a trick question
is it-
essentially, right?
What is that immature optimization? or not?
No, that's fine.
No, it's
No, it's fine. It's definitely fine.
Alright,
No, it's,
I'm joking.
you're not a smart ass. It's just fine. Everything's okay. No, you're right. You're absolutely right. It would be sufficient just to copy one and then you have full access to everything. Okay. What other bidirectional containers do we have? Standard list. What else do we have?
bidirectional.
There is another one, which is possible. Think about a tree data structure. If you have a tree data structure, it's called standard set, by the way, in standard map. We will talk about those. They are built in memory like this. You have a root, and you have a left and a right child. And that allows you to traverse that data structure with a bidirectional iterator, because each of those nodes not only points to the child, but each of the nodes points back to their parents. So you can bidirectionally traverse that data structure in 3 ways. What 3 ways can I traverse that data structure? Prefix and prefix. Right? So the first one, and I have colors. Yay, I have colors. First way to traverse is it's infix, prefix, right? I go to the previous one first. What's infix? It's a different sequence. And postfix would go to the last one first. Right? So depending on how you want to do that. So tree-based data structures are always bidirectional as well. And the last one, random access iterators. Any idea? I think you mentioned it already. What containers are random access? And the fact that standard vectors random access implies that the memory, oh, no, it doesn't really imply. It's
No, we can. They have different chunks.
right. The vector is random access. And here I have to add one thing. In theory, you could implement plus equals n on each of the iterators, just by repeating the operation n times. But the standard adds another restriction to the existence of that operation, namely a performance restriction. It says that this operation has to be order 1. So that operation should be independent of n. It should always take the same time. It should be O1. So no matter how far I jump ahead, it should require the same amount of time to perform that operation, which is not true for anything above the random access iterator, because here I have to repeat the operation n times, and it's clearly a linear dependency. It's not O1, it's O.
So an
Yes.
array is not a container because we can't change the size of it.
I haven't said anywhere that you have to change the size of an array.
Well, but you said all containers have to have specific, like being able to change, add to it.
Right, you're right. I said that.
So an
but
array is not.
There are arrays which are fixed size. There's one in the standard, by the way, which is standard array. And standard array is a template, and you say double, and it has 10 elements. So it's a compile time defined array, very much like a C array, where you have a fixed size. And you can use fixed size arrays in the very same way with algorithms, as long as they expose the properties of begin and end, because that's essentially all you need. Or they expose their own iterators, which represent their internals. And the trick here is, if we go back to that first picture we had here, where is it? That just means that essentially iterators know about the internals of containers. Because when the algorithm uses an iterator to refer to an element, that's nice and dandy. But the algorithm also will tell the iterator, hey, now move to the next element. And for that, the iterator has to know what type of container it points to, because it has to perform different operations depending on whether it is a vector where you have contiguous memory, or whether it's a list where it has to jump to the next element of the previous one. So the iterators are very specific to the containers, and that's why the iterator categories are very tightly coupled to the container categories. So if you have a bidirectional iterator, it probably will belong to a bidirectional container. And that's it. Okay? So far, so good. Lots of words around nothing essentially. So what I wanted to do next is to show you a small example of how all of that works together. And I have to press a button here, right?
Yeah, BGA.
Okay. Yeah. Yeah, works. So what I want to do is to write the copy algorithm in terms of, well, in the end, in the way how it's implemented in the standard library. Is that large enough for you? Is that? I think I can increase that size even further. Yeah, it's even better. Okay. So you probably all have implemented a copy algorithm already when you were writing C code. And that probably looked like this. Let me just write the body without the signature first. Let's assume we have two iterators, begin and end. Oh, well, let me write it, and I'll explain the syntax in a minute. Oh, let's call that in, out, void copy in begin, in end, out, O. Yeah, yeah, I'm seeing, I see it. I don't know why I decided to capitalize that. Okay. And the copy algorithm is essentially this. And you all have seen that, right? So let's assume we have, in the simplest case, pointers again. B and E point to a begin and the end of a memory range. And O points to a beginning of a memory range where we want to put stuff. Then the copy operation is really just a loop, which will iterate as long as B has not reached, the begin has not reached the end. And I dereference B, I dereference O, and I assign whatever B return, dereferencing of B returns to whatever O is dereferencing. So I dereference the two spots in memory. And after that, I increment those iterators by 1, which points makes them point to the next one. And I repeat until B reaches right off. And obviously that works for pointers, right? No tricky. But the beauty is it works for arbitrary iterators. As long as in is at least an input iterator and out is at least an output iterator. That's another step. We do comparison. B supports comparison. We talked about that, right? Input iterators allow us to compare things. Both input iterators and output iterators support dereferencing. Whereas input iterators support dereferencing only for reading, and output iterators support dereferencing only for writing. And both of them support ++. Move to the next element. Now, the template syntax is very specific to C++, and essentially just tells the compiler, I'm defining not a concrete function which is doing copy operation on concrete types like pointers, but I'm defining a template for a function. I'm just telling you how a copy function has to look like whenever I'm using it. And it also tells the compiler, please figure out what those concrete types are from the spot where I'm using the function. So let's do that in our main program. So let's say we define a standard vector of ints and we initialize it to some values. Okay. And I need to include a header file here. Okay. And I define another vector where I want to put that stuff in. And let's, for simplicity, let's call it in and out. For simplicity, let's say that that vector has 10. I can put 10 elements in it for now. I'll explain that in a bit. So let's just say that that vector has 10 space for 10 elements. Then I can use my copy algorithm just by saying in.begin, in.end, out.begin. Okay. So in is a vector which has 6 elements, and in.begin gives me the iterator to the first element, to the 1. And in.end gives me the iterator which points to the first element after the 6, the so-called end iterator. That's those two functions which every container exposes. Get to the first and to the last element, essentially, inside the container. And outBegin is a spot where we want to start putting data in. That's the first element of that out container. Okay? And now, what the compiler does, it looks at that copy, sees that I have a copy function template defined, but it doesn't know anything about what type in and out are. Is it a pointer to an int? Is it a iterator to something? Is it, I don't know what, some class which represents cars or whatever? But what the compiler now does, it says, okay, I know what type this construct has. It's an iterator which exposed from the vector. So it replaces that in with that whatever type I get here. And it replaces the out with whatever type I get from here. So the compiler deduces those types for us. Figures out what types is it. And thus, you can think of it like a macro replacement on the types here. Whatever type that is replaced, out is replaced by that, and whatever type in it, these two give me, it's replaced there. The only constraint I told the compiler is that the first and the second argument have to be the same.
Well, not the third, the same interest.
Well, because it might not be a vector, it could be a list, it could be whatever you want, right? All you require is that this is an output iterator, which has the properties of an output iterator, and it can be provided by any container. And we will replace that with a list in a second to show you how that works. Okay. So now we should be able to compile that. Let's compile it and run it. And then out should have six elements in it afterwards. But I will just, oh, doesn't like me. What did I do? Oh, okay, I shouldn't have called it copy. Let's call it my copy to avoid confusion. It just conflicts with the standard copy algorithm.
We don't have its copies in the standard names.
Yeah, but argument dependent lookup.
What?
ADL. The types of the arguments are in standard namespace, so the function in standard namespace are considered as overloads as well. But let's not talk about that. We'll get there. That's tricky business. We don't want to go there at this point. So let's just step through the code. Okay, I have my container, which has 6 elements, as you can see, 1 to 6. And now I just go into my copy algorithm, and I repeat that operation 6 times. And now my out container should have the 6 values in there, right? So what really happened is that the compiler figured out this data type for us and took the template, which is, well, like the English word template, right? It's like a rubber stamp. It's a description of how the function has to look like, and replaces it types, and then it generates a proper function based on the types and supplying to the compiler. And that's where generic programming comes in, and that's why Samuel said, hey, generic programming is templates. Because generic programming means I write code which is oblivious of concrete data types. And whenever I use that code, I instantiate the code for particular very concrete data types and let the compiler generate the code. Okay? So the trick here is, the question is, can I use copy with arbitrary types? Since the compiler figures out the types for us, right, and generates functions for arbitrary types, could I use it for arbitrary things?
We need an assignment.
Right, and not only, what operations do we need in order for the code to be well formed with regard to the input types? What do we need? We need to have a means of comparing two ins. We need to support the dereferencing and the ++ operation. For instance, when I just do the following. Let me do the following. Let me just comment that out. And now I'm going to be obnoxious. And I just say copy. And let's say I have an int I1 equals 0, I2 equals 3, and I4 equals 5. I could write this code, right? Formally, everything's fine. The first and the second argument have the same type. So the compiler should consider that function as an overload. But what will happen? Compiler will start complaining about what? We're complaining about that we don't have a dereferencing operator for ints. Let's see if that really happens. Here. Regional indirection. Just says that I can't perform that operations on the types you're giving me because in and out are in that case integers, right? I defined integers and was using integers as arguments. So the compiler was deducing integers, and it's telling us that it's deducing in as being an integer and out as being an integer. And here you have it explicitly written, right? See reference function template instantiation my copy int. So the two template arguments I'm supplying are int and int. And that can't work because ints don't support indirection. They don't support dereferencing. In other words, you can think of template code as duck typing. Template code is really just duck typing in some sense, because you're shoving in some things and it might actually work. But it will work only if all required operations which are used inside that particular function are supported by the types I'm using to instantiate that function. And this unfortunate feature is the reason why people complain about C++ template programming being so hard. Because if you ever have done template programming, you have stumbled over these error messages. Right? Megabytes of error messages from the fact that you forgot a semicolon somewhere. And the reason for that is that if you have a template function which is being called in a template function, which is being called in a template function, and which is being called in a template function, and that lowermost template function runs into an error like that, because one of the types you're passing through doesn't support the operation you requested to perform, it will tell you, yeah, I found an error there, and by the way, it's in the context of that thing, and it's in the context of that thing, and it's context of that thing. That gives you megabytes of error messages because the compiler tries to be helpful. It tries to tell you, hey, something went wrong, but I can't tell you what's wrong because you just showed something in here which I can't do anything with down here. Future versions of C++ will help because what they will introduce is what is called concepts. And concepts is a means of restricting the data type of a template function. So that you could say input iterator. The first argument has to be an input iterator in order for that function to be usable. And that allows the compiler to give you the error message in the top level. Because if you give it something which is not an input iterator, it will scream loudly on the uppermost level and not on the lowermost level. That will cut down the error message massively. So don't be afraid when you start using HPX, you will see these error messages. Don't say, wow. It's fairly easy to navigate those error messages. And you have to learn how to do that. And once you hit them, just tell somebody who already knows how to deal with them, and they will show you. The trick is to scan from top to bottom all lines until you find the word error. So because it's probably 20 lines down. And then you go back until you find the first line which refers to your code and look at that invocation, what's wrong there. Okay, so you have 20 lines of error messages. You go down until you find the first word error, go back until you see the instantiation context where your code starts showing up, because everything below will be HPX code. We don't care about that. Go up until you see your line, which you produced, and start thinking what you did wrong there. And that's where the error is. It's high probability. So don't get afraid when you see it. And the other thing is that C++ has a tendency to create snowballing error messages. So if one spot is erroneous, you get one error message for that spot. And it will trigger 100 other error messages afterwards, which are completely unrelated, which go away when you fix the first error. So never start with the last error in the list, and always start with the first one, because fixing that might already fix it. Well, usually it just gets you to the next one. That's the principle. Okay. So what we've seen is what a function template is. So you can write functions which are not expressed in terms of concrete types, but expressed in terms of categories, in terms of concepts. You can use that function with anything which is an input iterator and an output iterator. You don't care whether that input iterator comes from a vector or from a list or from whatever. For instance, let me just give you an example here. If I turn this into a list, and I need another include here. It will still compile and still run. Okay, I compile that. See, now I set my breakpoint and let it run. And you will see that I haven't even touched the copy function. All I did, I changed the type of the input container, which is not now not a vector anymore, but now it's a list. It's a bidirectional list which distributes these 6 nodes somewhere in memory. And this begin gives me an iterator to the first node in memory. And the ++ operation I am seeing, which is in the copy over there, the ++ operation will move to the next node in the list. Because the iterator, which I'm getting now, is a list iterator. It knows how to navigate the list data structure. Whereas the output is the same, it's still a vector, it still places elements consecutively in memory. That's why you get generic programming. You write a function once, you don't know what is actually used to invoke the function. The compiler figures out what data types are being used. You don't care about those, whether it's an apple or banana or whatever, as long as it supports these 3 operations, function will work. And the compiler generates a proper code from it, which is as optimal as it can get, because the compiler instantiates that function in the context of the list and the vector. So this function is as optimal as if you had it handwritten in the first place. There's no overhead for that abstraction, because everything happens at compiler. Compiler uses the proper types, uses the proper optimizations it can perform on all these types in the first place. Doesn't make sense? Yeah. So that's template functions, and that is a big piece of what we use in HPX. Async, we know and love, is nothing else than a template function, where all arguments are templates, all of them. But there are different restrictions to the template arguments you can use there. And if you use the wrong ones, you get these error messages. Everybody has already seen this. The technique is absolutely the same. And that's what we use everywhere in HPX, and that allows you to write the function once that allows HPX to deal with arbitrary arguments. No matter what arguments you supply, they will be used in the async operation or the data flow operation or in the future or back. Okay. Any questions? Questions? No?
Yeah, I have a question.
Yes.
I'm a little bit confused about in the concept. If we can mention that number 1, and in the honestly.
Why? Let's point to that one. It points to an imaginary element which is after the 6. So it will still copy the 6 because it will not be equal. It will be equal only once B reaches the element which is after the 6. Right? So there's a magic element in there you don't see, kind of, which is not there, but it's there. And only when you reach that element, you have copied all the elements. Other questions?
If we move from begin to end, let's say, if we have an iterator, move to the last element, and increment this again once, do we expect that we are still at this imaginary element and the comparison operator is work?
No. And iterators, doing anything to end iterators is undefined behavior. And undefined behavior in C++ is a very special thing. Undefined behavior, and the standard uses the term undefined behavior, means anything, the implementation is allowed to do anything at once. It can launch a rocket, it can do the right thing, it can crash, it can do nothing. Everything will be okay. It can print hello, happy birthday. Even that would be standard conforming behavior.
Listen, I wanted to ask, because I was not sure whether, for example, having carried over a pointer, I should take care of that and not increment after some.
You are not allowed to do anything beyond the end iterator.
I assume that if something that's happened is the fault on the side of the user.
Yes, it's your fault. I mean, you can increment the end iterator. You can do that if you want, but you're on your own.
Okay.
Right? The implementation is allowed to do whatever it wants. And write happy birthday or you're screwed or something. It would be standard conforming. And the standard is usually very strict about what's allowed and what's not. But undefined behavior is that loophole which is always placed into whenever, oh, you're on your own.
Wait, so we can't change the iterator? We won't have to change our container so that it has one more or one less element.
Well, then you get the new end iterator.
We have to create a new one.
Well, you call not end, and it will be with a proper one.
I'm saying if we're implementing our own. If we're implementing, I'm just thinking under the, or if you're implementing your own. Or iterator.
There's one thing which I haven't mentioned, namely that when you start inserting or deleting elements from a container, then depending on the container, existing iterators might get invalidated. Right? If you have a vector of 10 elements, and you remove, and you have an iterator to the first and to the 8th element, and you remove one element in the middle, the 5th one, which means that the upper 5 elements are moved one position in memory. And your iterators are still valid, but you will be surprised because that iterator now suddenly points to a different element. Right? Whereas when you remove an element from a list, and the iterators are stable, except for the iterator which points to the element you remove. Because nothing happens there, right? All you do, you remove the element and you adjust the pointers. So nothing else happens.
Just that element.
And that element doesn't exist anymore. You still might have an iterator, but it's invalid. You can't use it anymore because it points nowhere. It points to the root. And if you have a list out of 3 elements, you have an iterator pointing to the middle one. Removing an element from the list means you delete that element and you adjust the pointers to the neighboring elements so that they point to the previous one, to the next one, not to the one which you removed. So that means that the iterator which was pointing to the element you removed points into nowhere. It's like a dangling pointer. Right? When you take an address of a variable which doesn't exist, it's just undefined. And which iterators get invalidated depends on the container you're using, on the operation you're performing on the container, and so on. So some containers might give you stable iterators, others not. But that's very well defined in the standards. You can read about it, which of the operations make invalidated iterators. So generally, you shouldn't rely on iterators once you start adding or removing things from it. Or reordering elements, because then the iterators might be valid, but they point to different elements. And if you swap two of the elements, and the iterators just will be exchanged. They will point to the wrong element. You this kind of. A very good question. Yes. What I want to do next time, perhaps, is to talk about class templates, and function templates, and we have templates which you can build around types. So like standard vector, right? We've been using those. Those are class templates, and some data types which are templatized with an argument. So it's a list which can store integers. You can put any type here because that list can be used to store your data type features in there. Or simple like this and so on. And I will talk about how these things work. But for now, that's function templates, and they are very important. Yes.
Since this vector is integer, can we have the vector double?
Yeah. Oh, nobody prevents you from doing that. And it will store doubles if you do this. And will the code still compile? Any guesses?
Yes. Although
Will compile. Because I can implicitly assign an integer to a double, right? Because this operation now assigns an integer to a double, which is allowed. But if I do a, oh, let's compile it. You will see it.
Character.
Well, character will compile as well, but it might give a warning. So I can compile it, as you can see.
Oh, yes.
But what wouldn't work is if I put a, let's say, a string. It includes a string. And if I compile that, it will complain. No, it will not complain. Why didn't it complain?
Strings have iterated. I don't know.
Strings have a constructor where you can construct it from a single character. And it treated that as, and it was just so. It creates strings, 6 strings, where each of the strings contains one of those ASCII characters, which are smiley faces in this kind of thing. So it was a bad example. Let's do another vector. Vector. No, it will fail. Because you can't assign an integer to a vector. Now, this gives us an integer, and this gives us a vector of integers. And you can't assign an integer to a vector of integers. Compiler is complaining about that. And this already gives you a pre-taste of those error messages I was mentioning. As you can see, I have 100 lines of problems. But in that case, we are lucky. It says binary equal no operator found, which takes a right-hand operator of type int.
But you said that it worked string because there is a constructor in string taking one character.
Yes,
But there is a constructor in vector taking one int.
not the assignment.
So it's not constructor, it's assignment operator.
It's assignment operator. Oh, it's
That was-
assignment operator, right?
Yeah, of course.
It's not initialization, it's
Yeah.
assignment.
But now we have
Then you get some alternatives, and it tells you, yeah, they have considered the following functions, which actually are there, and none of them works. Could be standard vector and allocator, blah, 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 assignment. It could be that assignment operator, and so on and so on. None of those works with the right side of the side. So that is essentially what are the requirements, right? We require that these things are comparable, that B and O have a indirection and a plus plus, and that the type returned from B in the G reference is assignable to the type of whatever B returns. And the last constraint is not fulfilled. That's all. Okay. That's it. Good. Thank you. Thanks for your attention. You can cut that off.
Okay.